Hello everyone, welcome to the Landscapes Live online seminar series. We're going to start in a couple of minutes time. We're just going to let everyone filter through and then we'll start with today's talk. Thank you. Okay, welcome to today's Landscapes Live online seminar. Today I'm delighted to welcome Kathryn Fitzsimmons, who's going to talk about their research into dryland sediments and what it can tell us about landscapes through time. For those of you who haven't attended one of these seminars before, Kathryn will speak for about 45 minutes or up to, and then there'll be time for questions. We do ask that you don't post any of your questions, or rather the chat will be closed until Kathryn's finished speaking, and then we do welcome you to kind of put into the chat any of your questions. If you'd like to ask your question separately, then please raise your hand and we can welcome your questions then. Okay, so with that, thank you very much, Kathryn. We really appreciate you putting together this presentation, and really looking forward to hearing more about your recent research. Okay, thank you.
Thanks, Lizzie. This is our home, planet Earth. Its surface has provided our species with everything we need to survive. And we, in turn, seek to understand our surroundings, trying to find order and meaning in our world. This study of the Earth is geosciences. And this first image of our planet really does remind us of the vulnerability of our only home. Now, more than ever before, exploring geosciences from an integrated scientific approach is imperative. Now, as Earthlings, our first contact with the Earth is with the Earth's surface. So often that means engaging with sediments. And this goes some way to explaining why I was drawn to studying sedimentology and geomorphology in my undergrad. Specifically, I'm interested in deserts. After all, I come from Australia, which is the driest inhabited continent. Now, landscapes like dunefields, pictured here, can be beautiful and mesmerizing, but they also hold geological value. The unconsolidated sedimentary deposits in drylands preserve information about past conditions and interactions between the atmosphere and the Earth's surface. So it's this information that I'd like to explore with you today. So to that end, I'd like to provide you with some of my motivations for working in this field of research, and I'll provide you with a little bit of background. And it's probably not going to be a huge surprise to you that, after all, it's no secret that we're living in times of accelerating global climate change. The longer-term global observational data clearly illustrate this acceleration. So here in the top left, we have some NASA observations of temperature change, so the global temperature anomalies from September, the hottest year recorded, versus 1951 to 1980. And I'd like to just draw your attention to where the hotspots are. Many of those hotspots are actually in the deserts or on the desert margins of the world. On the bottom right, we have the change in drought severity measured by the Palmer Drought Severity Index over the last century and a bit. And again, we've got some hotspots, and where we've got the greatest increase in drought severity tends to be occurring on the desert margins of the world. So that goes some way to explaining my motivations for working in this field. Now, under accelerating global climate change, conditions in these marginal regions, like the edges of deserts, are likely to become increasingly unstable and unable to support human populations. Now, since deserts and desert margins, which I'm going to call drylands from now on, occupy about 50% of the world's landmass and host about 40% of the world's people, this increasing instability will become a central concern for the future. So the overall dryland area is set to increase substantially by the end of this century. There have been a number of studies which have been trying to model what this is going to happen, or how this is going to happen. And one of these is shown here in the bottom part, and also with the modeling of the total area of drylands as it's set to expand over the next century. What this means is that up to 2 billion people are going to be placed under extreme water and resource stress if we breach the 4-degree warming scenario, as shown in the bottom right. So these model-based visualizations help to emphasize the importance of better understanding the interactions between the Earth's surface part of the geosphere, along with the climate and the hydrosphere. So the question that I'm interested in exploring is what sorts of landscape responses the future might hold. Now, as geoscientists, we know that in order to understand trajectories of future change, we need to understand the nature of landscape change. We need to know what sort of landscape is possible. We need to know what sorts of landscapes have been inherited from past climatic situations. So to draw your attention to a specific example here, I've got an image of the present day and rewound that back to the last glacial maximum about 20,000 years ago. Now, one thing that many of you will be aware of is that there were lowered sea levels during this time. There were vastly expanded ice sheets and glaciers. But something that perhaps you're less familiar with is the fact that during these last ice age periods, we also had vastly expanded desert regions. So what that means is that the present day margins of deserts are effectively fossil deserts, which could, if they breach a threshold, become reactivated and become deserts in the future. So that's one of the main driving questions which I have in my research, namely, what can dryland sediments tell us about hydroclimate and interactions between the atmosphere and the Earth's surface over a range of temporal and spatial scales? So I'd like to structure my talk in 2 parts, mainly. I would like to explore a little bit about looking at sediments through time and what we can develop in terms of chronological frameworks for change in sedimentary environments in drylands. And specifically, I work with luminescence dating as a major tool. And secondly, I'd like to take a look at sediments on the move. So what kind of information we can get about sediment transport, the provenance of sediments, where they're coming from and where they're landing, and what their relationship is to climate. So ultimately, if we put these two together, we can start to get some perspectives on hydroclimate and atmospheric circulation, what the sediments can tell us about these things. So I've worked in many dryland regions of the world, but today I'm going to be focusing on my work in Australia, although some of my work from Central Asia will also trickle in. So why focus on Australia? Well, it is the driest inhabited continent on Earth, and that makes it an enormous and fascinating natural laboratory for exploring different aspects of dryland sedimentology. So to the first of my research foci for today, I'd like to take a look at sediments in time and what we can do to generate chronological frameworks for past environmental change in drylands based on sedimentological information. So for that, I'm going to be focusing on the Quaternary period, the last 2.6 million years, and more precisely, I'm going to be looking at the latter part of the Quaternary, so the Pleistocene and the Holocene to some extent. And Here I would like to introduce you to an important tool for this research question. So here we're going to be looking at luminescence dating. Now this is an absolute dating technique, which is based on the physical properties of crystalline minerals. Now, crystals are natural materials, so that means they're imperfect. So that means they contain within them defects within the crystal lattice. And within these defects, charge can be stored, a little bit like a battery. So if you expose your minerals to sunlight, for example, through sediment transport or heat or friction through earthquakes, this will result in release of the stored charge, and this will deplete your battery. So then your clock will start. As the mineral grains are deposited and buried, the ionizing radiation which is present in the surrounding sediment will facilitate the trapping of charge in the defects in the crystal lattice again. Now, the rate at which this charge builds up is proportional to the amount of ionizing radiation which is present in the surrounding environment. So this is 1/2 of our age equation, what we call the radiation dose rate. Now, the amount of charge which has built up in our crystal lattice since burial is measured in the form of recombined energy, which is released as photons of light. This is the phenomenon known as luminescence. So these photons of light, this recombined energy, is released as the mineral grain is exposed to sunlight or friction or heat. So we can measure those photons of light, and that is proportional to the amount of radiation which has been received to the sediment since it was buried. So this gives us the second half of our age equation, the radiation dose to the sediment. So what we need to do, of course, is be careful to sample our sediment grains in light-proof tubes to prepare them for measurement in the dark. A few fast facts. Luminescence can be applied basically wherever there are unconsolidated sediments which have been deposited and buried. Most of the time we're working with quartz and feldspar minerals. We can date zinc grains and aliquots of grains. We can date materials which are very close to modern through to about 500,000 years or more, and the uncertainty is about 5 to 10%. So when I first started in this field of research, I was working on linear dunes in the most arid core of Australia, shown here on the left-hand side. Now, linear dunes are the most common type of sand dune in Australia, and they're thought to form broadly parallel to the resultant sand shifting wind vectors. So in this study, we undertook a temporal framework for aridity based on phases of dune activity, which was generated from the luminescence dating using single grains and single aliquots. Now, from this, I was able to generate a relative probability distribution function for periods, to identify periods of linear dune activity in the central part of Australia. And we were able to identify statistical age peaks, which I then tried to match up with records of things like dust flux in the Tasman Sea and dust flux to the Antarctic ice records. And as you can see, some of these peaks match up and some of these peaks don't match up quite so nicely. So you can argue that it was with mixed success. And probably one of the reasons for that is that the mechanisms for sediment transport, for the generation of sediments, maybe doesn't necessarily match up with the central part of the Australian continent compared with the Antarctic ice dust, which is maybe coming from somewhere else and they're related to different kinds of processes. So to get a slightly less ambiguous picture, I started moving towards the desert margins. So I was rationalizing that sediments on the edges of deserts might give us a less ambiguous picture of the expansion and contraction of the arid zone and the climatic mechanisms associated with that. So to that end, I started working on what are called lunette dunes. Now, lunette dunes are transverse shoreline dunes, which are common on the desert margins of Australia. And you can see these are shown in this map by Paul Hesse from 2010. So effectively, most of the time, since they're on the semi-arid margins, most of these lunettes are actually associated with lakes which periodically fill and dry through time. They're not full all of the time. So what that means is that we can interrogate the sediments within the stratigraphy of these lunette dunes to give us information about hydroclimate or perhaps about lake hydrology, depending on the catchment. So when we're looking at a lunette dune, we can look at we observe different sedimentary types or facies within that lunette dune. Now, I'll explain to you 3 different scenarios, which are the main end members of what we were looking at within the lunette dune sediments. So if you have a semi-arid zone and you get periodic filling of your lake, you have a lake full stage. So what this means is there is water in your lake all of the time, there is wind blowing across the fetch of the lake, you then have a beach forming, you've got nice rounded quartz sands. This is an environment where there's it's fairly texturally and compositionally mature, so we're dealing mostly with quartz, not a lot of feldspar present. So you'll then get a dune building downwind of that, a little bit like what you get at the coast. And this is transverse to the wind direction. So it's at a 90-degree angle to the wind direction. So I've included here also some evidence about human traces. So you've got people living in these landscapes, interacting with the full lake conditions, with the fact that there's water in the landscape, leaving their traces, burying their dead, and these get recorded and preserved within your sandy lunette dune. If you then move to a stage where the lake isn't full anymore and you've got a drying stage, you then start to get exposure of the lake floor. Now, the lake floor typically has finer grained materials, and it also has salts. Now, what happens on the exposed lake floor in these sorts of conditions is a process known as efflorescence. So you start to get aggregation of these clays and salts together to form sand-sized clay pellets. Now, these sand-sized clay pellets then behave like a quartz sand grain would. So they then get blown up onto the lunette dune, along with quartz sands and things as well, to form what we call a saline clay dune or a paletal clay dune. Now, again, we've got people living in the landscape, leaving their traces, interacting with the landscape in different ways because there are different sorts of resources present in the landscape. And you also get partial removal of the underlying stratigraphy as well. Now, there's a third end member or a third scenario, and that's what we call the soil formation stage. Now, this is when the lake is completely retreated, but locally you may have relatively wet conditions. So you'll tend to have the formation of soils over the top of your lunette dune, as well as to some extent over the top of the lake floor as well. And this will result in some infiltration and concentration of clays, the precipitation of calcium carbonate nodules or mottling. You'll get a more oxidized horizon. So these then get built up into a stratigraphy where you get these different phases preserved within the sediments. Now, if you're looking to reconstruct hydroclimate in this sort of environment, rather than looking at the lake floor, which is an area where you often get removal of the sediment by deflation, the best place for reconstructing hydrologic activity is in your lunette, because this is actually preserving as a kind of proxy for what's going on with the story of lake filling and drying. Now, let's move to a specific example where I've been working for many years. This is an area known as the Willandra Lakes World Heritage Area. Now, in terms of location, it's sitting in the semi-arid zone of southeastern Australia, as you can see in the top left here. And it's a very large catchment, which isn't flowing anymore. The headwaters of the catchment are actually about 800 kilometres away in the highlands of eastern Australia. And these highlands are temperate subhumid. So basically, in order to fill the Willandra Lakes, we had to have rainfall and runoff flowing through the Lachlan River into its distributary, the Willandra Creek, and then flowing into this nest of multiple lake systems, these overflow lakes. So each of these lakes preserves a lunette within it, on its eastern margins. But where I've done most of the work is at Lake Mungo. Now, Lake Mungo is an important place, not only because it's one of the best preserved long-term, almost continuous environmental records of sedimentary accumulation, but it also happens to be really important for human evolution. It's the site where we've got the oldest known ritual burial in the world. It's about 42,000 years old. So it's a really important place where we have preservation of environmental information as well as human and archaeological information. It's a beautiful place to work, as you can see here, but it's also very challenging because we've got very substantial erosion taking place. And the reason for this is because when Europeans arrived in this part of the world about 150 years ago, they brought with them cloven-hoofed animals and rabbits, and this change in land use and the trampling of the sand dune, the lunettes, by these pastoral animals, meant that we've got quite a lot of erosion taking place. So it's a bit of a jigsaw sticking together the sedimentological information to reconstruct the hydrologic history over long periods of time. Nevertheless, it's possible. So how do you develop a framework for lake filling and drying? Well, as an example here, I've got Lake Mungo. Now, what we did was we undertook multiple stratigraphic transects, and you can see the locations of these along the lunette in the top left-hand side. And we mapped the exposures of stratigraphic units in 3 dimensions using, with the help of air photos, digital GPS, and a lot of field work. And then we added the 4th dimension, so the time, with luminescence dating. So where we've got the dots are where we've got luminescence dating samples. Now I'll go into a little bit more detail for what we actually found. So we identified 11 different stratigraphic units. 5 of these units clearly relate to lake hydrology, and these are shown here. So we've got some photos of what the exposures look like on the left-hand side, and then on the right-hand side, we've got some thin section microscopy showing what the sediments actually look like. So we've got 3 lake full events, the 2 at the bottom, and then there's the mega lake in the middle there. And these are nice rounded quartz sands. We do have in the bottommost unit, we've got an increased accumulation of clays and carbonates as a result of a very strongly developed soil. But basically, we're looking at nice rounded beach sands. And then we've got 2 what we call oscillating lake events, where we've got periodic lake filling and drying. And that lake drying is expressed in the form of paletal clays, which are very frequent, which have kind of coalesced together as a result of rainfall. They sort of collapse. But these show that we've got 2 phases where we've got oscillating drying lake conditions. We also have 6 stratigraphic units which represent reactivation after the Willandra Creek ceased to flow. And we think that it ceased to flow about 15,000 years ago, and we think that that was because of tectonic activity. Now, any reactivation of stratigraphic units after that time is going to reflect conditions not in the headwaters of the catchment, but rather locally. So we've got multiple units which represent reactivation as a result of aeolian processes. So this suggests that we've got short-lived dry phases after lake retreat. And then we also have some sheet wash processes. So from unconstrained flow down the lunette, which suggests that there were relatively wet conditions taking place. So we've got 11 different stratigraphic units defined. Now, amongst these investigations, we found a few surprises, and I'd just like to shed a little spotlight on one of these surprises. Now, we observed a stratigraphic unit with rounded allochthonous gravels. And as you can see in the bottom right there, these gravels are made out of rocks like silcrites, which are from nowhere near there. So they must be from far traveled processes. Furthermore, they're very rounded. They look very much like shoreline gravels, which have been washed into the lake system. But where this starts to be perplexing is the fact that these gravels are occurring some 5 vertical meters above what was generally accepted to be the lake fill level as a result of previous studies. So I needed to convince myself that this was indeed a shoreline and that it wasn't just an isolated occurrence in that particular exposure. So what I did was we surveyed outcrops of the shoreline gravels along a 3-kilometer transect using digital GPS, as you can see in the top left there. And we found that universally these exposures of gravels were occurring at the same level, about 75 meters above Australian height datum. And then we also went over onto the western side of the lake, and we undertook 8 different DGPS transects of the landscape. And here we observed wave cut benching at what we accepted to be the main shoreline level, so 68 to 70 meters above Australian height datum. But then we also saw wave cut benching at 75 meters. So this is at the same level as our gravels on the eastern side. So this started to convince us that we had a hitherto unidentified shoreline, which was sitting about 5 vertical meters higher than the previous fill line. Now, of course, we wanted to know how old that shoreline was. So we dated this stratigraphic unit. So we focused on the sands which were forming a beach dune above the gravels. And this came to around about 24,000 years ago. So this is a time period just prior to the last glacial maximum. And then we flooded the digital elevation model and we were able to quantify an increase in lake volume of about 250% above the normal filling events. In addition, some of the lunette would have actually been cut off. If you look at that inset on the top right, labeled C, it would have created an island on the lunette in the northern part. Now, this has a number of implications. Firstly, in terms of hydroclimate. Now, this was a time period just prior to the last ice age. This must have been a time when there was much more water in the system. So that was probably related to an increase in catchment rainfall over a short period of time, an increase in runoff, which may have been related to decrease in vegetation cover. This was also at a time when temperatures were decreasing as we were moving down into the last glacial maximum. We also would have had, with decreasing temperatures, reduced evaporation and a reduction in vegetation cover. So this would have contributed to that increased runoff. And this was very, very short-lived time span, as I mentioned. Then we finally hit the last glacial maximum. There are also some interesting implications for people who were living in this landscape at the time. There is evidence of many hearths at different levels within that stratigraphic unit on that island area. So what this means is that people repeatedly access the island. The thing is, though, our digital elevation model, as flooded, shows that they couldn't have walked there. The water must have been at least 2 meters deep. So the question is, well, how did they actually get across to the island? Why did they go there? Did they start to resurrect watercraft technologies 24,000 years ago in the middle of the Australian desert, more or less? It throws up a few interesting questions, which will hopefully be answered in the coming years. Okay, so now that we've taken a look at one particular time slice, let's step back to take a look at the longer term picture of lake filling and drying prior to that final lake retreat at around about 14,000 years ago. So for this, we've got a chronology based on 126 luminescence ages, coupled single grain and single aliquot. And this is over 4 different lake basins. Now we show this here as a probability density function, and we compare this with the Greenland ice curve and with the oxygen isotope stages. So I'll walk you through it. So firstly, from about 40 to 60,000 years ago, this is the time period which coincides with the earliest dated human occupation of the region. But we do also seem to have sort of two humps in the chronology of this stratigraphic unit, which suggests that perhaps we've got two filling events which hadn't previously been identified. After this, from 40 to 29,000 years, we have a drying lake event, which is shown expressed in the form of oscillating, so paletal clay dunes laminated with sandy lamina. This is followed by a period of soil formation, where it appears that the lake was completely dry, but locally the conditions were wet enough that we had a soil forming on the surface. Followed by our mega lake, which dates to about 24,000 years, which precedes the lake drying from about 24 to 17,000 years and spans the full last glacial maximum. Now, after that final lake retreat, we had those 6 additional stratigraphic units, which tell us about local climate. So here we've again got probability density functions, which show when we've got periods of wet conditions and periods of relatively dry conditions. So we've got a couple of dry phases and a couple of relatively wet phases. And furthermore, we also have some ages from the last 250 years. And I say here that this is quite extraordinary, and this is a reflection of the fact that the Australian quartz is really, really bright and gives enough of a signal that we can actually date single grains to the 1940s. So we have a number of ages from a reactivated aeolian deposit, which is 3 meters thick, which coincides with the 1940s drought. So this is a documented drought after European arrival, which was also a time when we had rabbit plagues, where there was substantial erosion documented. If you want to see the erosion and the rabbit plagues, look on YouTube. There's lots of old footage of this sort of thing happening. It's really quite exciting that we've been able to date this with luminescence dating, but it also shows that there has been substantial change in the landscape relating to drought, but also to land use after European arrival. So I've been able to show you the frameworks that we've been able to develop for the lake lunette systems in the Willandra. It's a work in progress, and at the moment we're trying to better understand how the catchment hydrology works with respect to how climate influences hydrologic connectivity and lake filling and drying. So we're taking a look at how the lakes could be flooding under the present day climate, and then the next steps are looking into the past. But this is very much a collaboration between myself and my postdoc, Kanchan Mishra, who is based here in Tübingen, and Markus Fischer, who is based in Potsdam. They're really the brains behind this, but hopefully we'll get a better understanding of how the system works on a catchment scale. So take-home messages from our work on sediments in time. Well, in dryland contexts especially, we need to integrate a range of different environmental traces over landscape scales. Luminescence is a fantastic and optimal dating method for this context. The Australian quartz signals are bright enough even to date Anthropocene materials, and the dose rates are also low enough that we can reliably extend our dating timeframe beyond the last interglacial at 100,000 years. The next steps are going to be to link this sedimentary information with hydrologic and climatic models to better understand how the systems work, and ultimately to better understand the thresholds for their reactivation under future scenarios. So now we'll move on to the second focus of this talk, to take a look at what sediment transport can tell us about interactions between the land surface and the atmosphere. So to do this, we're going to take a look at modern wind regimes at the surface, so looking at sand transport, dune activity, and at altitude, so looking at pathway models and dust trajectories. And then we'll take a look at provenance, so what information we can get about sediment sourcing, and some exciting new methods which my colleagues are working on developing. So let's return again briefly to the Willandra Lakes. So in this case, I'd like to take a look at the morphology of the transverse lunette dunes. Now, I mentioned right at the very beginning that lunate dunes are transverse. So we have, therefore, an assumption that the accumulation of sediment on a lunate dune is going to be thickest along the part of the dune which is perpendicular, so 90 degrees to the prevailing wind vector. So I covered a lot of ground on foot in the Willandra lunettes over the past years. And what I observed was that there are certain stratigraphic units which are thicker in certain parts of the dune than in others. So take, for example, the 24,000-year-old megalake deposits. And I find that these are thicker in the northern parts of the lakes. And you can see two examples here from Lake Mungo and Lake Durfong, whereas the last glacial maximum age deposits are thicker in the central parts. So the implication here is that potentially we've got a change in wind regime over time. So from 24,000 years, we had a slightly more southerly vector, which shifted during the last glacial maximum to a more westerly trajectory. Now, the question is, can we find clues to past atmospheric circulation in sediments in other parts of southeastern Australia? So for that, I'd like to introduce another site, and that site is called Spring Creek, and it's in Western Victoria, so it's further south from our Willandra Lakes, on the Western Victorian basalt plains. Now, the Western Victorian basalt plains are the third largest active volcanic province in the world, and this particular site is sitting smack bang in the middle of those basalt plains. It's basically basalt wherever you go. Now, despite the fact that there is no outcrop of quartz sand anywhere within this site, within a 50-kilometre radius of this site, I was looking at this site for a different question, but I observed clayey quartz-bearing silts, which I was able to date from around about 29,000 years. And these become more quartz-rich and more sandy after about 25,000 years. Now, like I say, the reason why I was doing fieldwork there was actually for a different reason. So I never took the samples, but I did this year. So I don't actually have any ages for this sandy silt at the top. Nevertheless, we will get some ages out in the coming years, but what this implies is that we're looking at sandy silts which post-date 25,000 years. It's not a long stretch of the imagination to hypothesize that perhaps these are last glacial maximum in age. So we've got quartz and it's sitting on top of basalt, and the nearest quartz is 50 kilometres to the south or to the west of our location. So how did this quartz sand get here? So my bet was on aeolian transport. And what this suggests is that perhaps we had more intense westerly winds intensifying over the time period that these sediments were deposited at Spring Creek. So I teamed up with an atmospheric scientist from Mainz, Sergei Gromov, to take a look at wind regimes and particle transport trajectories. And we compared what we get from the present day using climate reanalysis with some particle trajectories which are derived from climate models for the last glacial maximum time slice. So what we observe, and these particle trajectories shown on the left-hand side, are particle trajectories for the 120 micron size fraction, so sand size material, and arriving at the Spring Creek site on the left and at the Willandra Lakes on the right. And the brighter colours basically tell us the greater likelihood of where that sand is coming from, of that particular size fraction. So if we look at the present day, we can see that there is a great deal of local transport of sand size material. In particular, when we look at the Willandra Lakes, we've got a kind of southwesterly trajectory of the winds. Now, if we rewind back to the last glacial maximum, and we look at Spring Creek, and we compare that with the present day, what we can see is that there is a very much stronger imprint of westerly transport, so coming from the west, arriving at Spring Creek. In addition, we have a stronger westerly component to the winds arriving at the Willandra Lakes during the last glacial maximum as well, which might explain why we've got that westerly morphology of the LGM age stratigraphy in the Willandra Lakes lunettes. So what this suggests is that we've got stronger near-surface westerly winds onto the continent during the last glacial maximum. That means there's a stronger potential for distal aeolian transport onto the basalt plains, and we've got enhanced aeolian activity in the semi-arid zone around the Willandra Lakes. So basically, the last glacial maximum was likely to have been windy and dusty. Now, all this exploitation of dune morphology to infer wind trajectories makes me start wondering again about linear dunes. Now, after all, from this map by Paul Hesse, we can see that some 40% of the Australian mainland is covered by linear dunes, which, as I mentioned earlier, are thought to form broadly parallel to the sand shifting wind vector. So just imagine if we could interrogate those linear dunes to give us information about past wind regimes. This would be a huge project, and we also need to think about how old the different dunes are and whether there is some kind of inertia in the morphology and the orientation of the dunes. So where would you start with this kind of question? Well, first thing that we would need to do would be to map the morphology of the dunes and to investigate their interaction of their morphology with other landform types. Now, this is a task in itself, but one which has moved forward in leaps and bounds beyond the work which I did during my PhD, where I had to do everything manually, working with ASTA imagery and manual digitization of the linear dunes. Nowadays, we've got all sorts of exciting new tools, including semi-automated mapping using open source software and open source data. Like this work from Southwestern Lake Eyre, Katitanda, which was done by my bachelor student, Lorenz Fischer, who just published his work. And from this, we can get information about aggregate morphologies and particularly orientations, spacing between the dunes, frequency of Y junctions, so merging between the dune forms, and also information about their interaction with other landscape forms like channels or lakes, for example. Now, another approach would be to take a look at very recent or modern linear dunes and their relationship with wind regimes to test this idea that these things do indeed form parallel to the resultant vector of the sand shifting winds. Now, for this exercise, the Australian dunes are definitely too old, as we saw from the first slide where we looked at my PhD work. So for here, I'm going to shift continents and I'm going to move to Central Asia. And specifically, I'm going to take a look at southeastern Kazakhstan, where we have really large, recently deposited dune fields. So we established that these dunes were formed over the last couple of thousand years. And then we took a look at dune morphology. And this was work which was done by Maika Nowatzki, who's a PhD student at Oxford. She was a master's student at Tübingen with me. And she mapped the dunes using semi-automated mapping of the morphology. So mostly she was looking at dune orientation. And then we compared this with wind regime statistics based on the ERA 5 climate reanalysis data set from the European Centre for Medium Range Weather Forecast. So here we took a look at surface wind seasonality, and we observed that we have very frequent northerly winds. Now we look at the context of this particular dune field in southeastern Kazakhstan, and we see that the Ili River is sitting more or less to the north of that dune field. And the Ili River has a great deal of bed load, which provides potential sediment supply. So we could potentially infer here that the northerly winds are responsible for sediment supply. On the other hand, we have a combination here of linear dunes, and these are mostly east-west in orientation, and transverse dunes, which are north-south in orientation, as you can see here. Now, what then is driving the orientation of the dunes? Now, when we look at the wind speed, we observe that the strongest winds are actually coming from the west. So this suggests that the dune orientation and the morphology of the dunes is actually driven by the strongest winds, which are coming from the west. So there's a great deal of potential in exploring this hypothesis, and we're exploring this in a little bit more detail, but it's a work in progress. But definitely it's a hypothesis worth taking a look at. Now, so much for dunes. These give us information about near surface transport and airflow, and this is susceptible to interaction with other surface features and topography. So now I'd like to take a look at dust. Well, dust is finer grained, it's higher altitude transport, and it's got a greater potential to link with large-scale climate circulation. So I'll continue with a little bit more detail about Central Asia now, because this is a region where we've got a lot of dust deposits on the piedmonts of the Central Asian high mountains, and it's a nice lateral laboratory for exploring these links. It also happens to be at a sensitive transition zone between major climate subsystems, namely the westerlies, the Siberian high and the polar jets associated with that, and the monsoonal systems, which are coming from the south and the southeast. Now, these are regions which have very thick deposits of windblown dust, or loess, and these form very thick deposits which reflect the glacial interglacial changes. As you can see here in Karamaydan from Tajikistan, it's a site where we're working, and you can see that we've got primary generation of dust and accumulation of dust during the glacial phases, and during the interglacials we have accumulation and accretion of soils, as you can see from the darker layers here. So let's take a look at dust transport and the potential links between loess and climate circulation. So here we're using climate reanalysis with particle trajectory models. And again, we've got the brightest colors, which are reflecting the greatest probability that the sediment is coming from that area. And our red spot here is the loess deposit where we're interested in. Now, this particle trajectory model suggests that we've got a lot of local transport, as shown by the bright colors just around the area, but we also have a very strong westerly component, and we also have some degree of northerly transport as well. So this leads me to the idea of provenance. So this is the idea where we're using characteristics of source rocks to fingerprint the sedimentary deposits. And in the Aeolian context, we can get a vector for the sediment transport. So we can start to get information about climate circulation. So here we're taking a look at southeastern Kazakhstan again. And here we've got that model from the previous slide where we've got westerlies, northerlies, and local winds, which are acting on this region. So we're working with Aditi Dave, who was my PhD student, is now a postdoc in Romania, and Alida Timagabo's group, also in Romania, to develop a new method for provenance using trap charge in quartz. So if you remember, the luminescence is based on the principle of charge trapped within defects within the crystal lattice. Well, some of those defects relate to different geometries in the molecular linkages of the quartz. Now, the formation of certain defect types in the quartz, known as E', appear to increase in frequency with the age of a rock. Now, you can measure that with electron spin resonance and start to explore whether you've potentially got a provenancing tool here. Now, this was work done by Aditi Dave in her PhD, where she compared the Tajik loess with the Kazakh loess, and she observed some very striking differences. She investigated the E' intensity, which is one of those defects, and showed that loess from the two ends of the Central Asian high mountains, so from Tajikistan and Kazakhstan, have striking differences in the E' intensity. Now, when we think about the likely source rocks, we can see that the Tian Shan rocks are very much older. This is where we've got the higher E' intensity and in the loess, and the higher likelihood that we've got older rocks which are contributing to our sediments. And the reverse is the case for our Tajik stuff. So this suggests that we've got a potential exciting new tool for working with quartz electron spin resonance and the defects within the crystal lattice as a tool to reconstruct the provenance of our aeolian deposits. Now, it's a tool which works with quartz, which is a ubiquitous mineral. It's pretty much everywhere in the sedimentary systems. It's not something which is restricted to aeolian deposits at all. But it's certainly something which we're really excited about exploring in future. Now, I'm going to fast forward here and leave you with a couple of take-home messages from Sediments on the Move. So here it's again important to integrate different earth science techniques, GIS and cartography, climate reanalysis, dust trajectory analysis, and these integrated techniques can help us inform us about the role of surface winds in geomorphology, as well as understanding the higher altitude distal processes and the links between dust transport pathways and climate circulation. And then there's also this exciting steps towards a quartz-based trap charge method for sediment provenancing. It's got potential for all sorts of different sedimentary environments, which basically means the landscapes. So it's a really exciting tool which we're looking forward to exploring in future. So for that, I'd like to thank you. I'd like to thank the members of my current group in Tübingen, the members of my old Max Planck research group in Mainz, my cooperation partners around the world, and particularly to the many Indigenous groups, including the Mari Mari, the Bargadji, and the Nyampo from the Land Lakes region, who have welcomed me to country. Thank you.
Thank you very much, Kathryn. That was a really, really interesting talk. Really cool. You took us right around the world there with that. So thank you very much. So just to let everybody know, the chat is open. So please post your questions for Kathryn there. We've got about 5 minutes to ask Kathryn whatever questions we have. I can start while people think about what they'd like to ask you. I was interested, I'll sort of take back to the sort of first part of your talk, looking at Australia. I was interested when you said about sort of at the point at which Europeans migrated to the continent that we see elevated rates of erosion. And I'm just wondering, has that actually been quantified? And also then what methods perhaps have been used to do that?
Yes, there has been work done, not by myself. I mean, the Land Lakes is the only example where I've done any work in this, but there are colleagues of mine based in Australia who have focused on influx to oxbow lakes and to fluvial deposits, and they've been able to quantify. Well, they've got nice high resolution age models working with lead-210 and cesium. And quantifying and characterizing the sediments, quantifying the chemistry and the amount of material. There are enormous amounts of sediment which have been mobilized and deposited in the last 200 years since the Europeans arrived. Another marker which I should add is pine pollen, which of course is not indigenous to Australia. So the moment that appears in the sedimentary record, and these oxbow lakes are quite handy for understanding that sort of system, right? Because they're quite stable, they don't get removed. So when that appears, that's basically, okay, that's the bottom of the arrival of Europeans in the area. Yeah, huge amounts of sediment have been mobilized and deposited and have been exported out into the oceans by the big rivers. Yeah, not so much work in other parts of the continent. That's where most of the work has been concentrated. But yeah, I mean, it's definitely a very active space for research.
Cool. Thank you very much. Thank you. Does anybody else have any questions?
I'd like to quickly say if anybody would rather ask their question out loud, just raise your hand using the reaction button at the bottom of your screen, and we'll unmute you. But otherwise, I'm going to ask. I mean, it's maybe a bit of a naive question. I was really interested what you showed last about provenance tracing using OSL, and I was wondering, how do you think different transport method could impact this signal that you were showing, that you were using, right? So like aeolian versus fluvial or things like that.
Potentially. I mean, we know that things like luminescence sensitivity, so the ability of charge to be transferred between the defects in the crystal lattice, that does change over sedimentary history, and it potentially also changes with modes of transport. Yeah, in terms of the E prime. I don't want to say anything wrong here because I'm not sure if Aditi is in the audience. She would certainly be able to answer that. I mean, we've been hoping that this is a fairly stable signal. Yeah, but as Nguyen has shown, the luminescence characteristics do change downstream, for example. So within a given sedimentary system, the luminescence properties will change. Whether the E prime is something which changes substantially in the transport process is something we hope doesn't happen too much, but I hope that Aditi or if Alida is in the audience might be able to answer that more precisely.
Okay, thank you very much. Do we have any other questions for Kathryn? We've got a couple, maybe time for one more. No? Okay, well, I've got one final one then, Kathryn, and then maybe we can draw the session to a close. So it was just, I was really interested to hear you talk about the fact that you've been able to use OSL over such short timescales. And I mean, that has sort of massive implications for, you know, potentially applying that method, you know, sort of on the decadal timescale, I guess. Is that what sort of you're arguing? I just wonder, like, as a novice to OSL, you know, what you mentioned that maybe it's only applicable then in locations like where you were working, but like, I mean, where else might you be able to apply this approach and be able to capture processes and change over kind of the last 100 years, I guess? Like, what am I looking for in terms of where I can sample, basically?
I think the prevailing hypothesis as why this works in Australian sediments is because the Australian landscape is really, really old. So what that means is that the sediments which are sitting on the Australian landscape have gone through many, many, many cycles of reworking and deposition. Now those repeated cycles serve to what we call sensitize the signal. So this means that you get a brighter signal, a more efficient charge transfer, so to speak. So that's the reason people think why the Australian quartz works really well. But I will say that it doesn't work really well everywhere on the Australian continent. Like, it is a big continent. So I guess if you're interested in looking at super young samples, super young sediments and dating those with luminescence, you would need to look at a context where there is has been a very long sedimentary history. So I guess places like Brazil or the Craton areas may be one place where this sort of thing might work. That said, you know, if you there are things like portable luminescence readers, which you can measure almost instantaneously whether you get any signal out. So if you have access to one of those sorts of things, whether it's in the field or in the lab afterwards, you can find out very quickly and very easily whether you've got any measurable signal in there and whether it's worth moving on. Right. The dating.
Okay, thank you very much. Yeah, that's really interesting. Okay, I'm conscious of time, so I just wanted to sort of thank you again, Kathryn. Really, really appreciate your time today and the effort that you put into your presentation. It's really, really great to hear more about your work. So thank you very much. And so with that, I'd like to close the session and advertise next week's session, which is fronted by Joel Scheingross, and they're going to talk about, it's a three speakers, which is sort of slightly novel for Landscapes Live. We've also got Marissa and then also Niels Hovius from the GFZ that are going to be speaking, and they're going to talk about some of their work. Where are they located? I can't remember now. In the Andean Fallen Basin. So looking forward to that talk. But thank you very much, Kathryn. Really, really appreciate it. Thank you.
Thanks for inviting me. Thanks.
All right, I'm gonna take off. Great seeing you.
Hi, Pedro.
Hey.
I was wondering, can you technically kick people out of a Zoom conversation? Never tried it.
Yeah, no, I just did.
I think it's people who probably like left it on. I've done it before, like
Right,
listening to talk while whatever, washing the dishes or something.
Right.
And,
Yeah, it comes up as automatically that it wants you to report them. So then you have to make sure that you don't report them to Zoom.
Oh yeah. Fair. Yeah, that didn't do anything. Yeah.